Alright, today we continue with differential equations, so that's application of differential equation. So again, you need to differentiate and anti-differentiate. And with this is you're gonna have different scenario with a technical language to relate to certain situation. Okay, so first example is you would have a table like this. So you have your uh, derivative, the first derivative that has a value for a value of t, and you need to recognize this pattern. So you can see it's for an incremental, a linear increment of t, the derivative is following a different pattern. Okay, so here you need to relate what it is. Any of you have an idea what pattern it could be? It's obviously not going to be linear. Yes, exponential. Okay, so it's let's say a to the power of t, and the base you can figure it out. Okay, how does it work? So you can see it's not a exponential, but it's pretty close. It's a square times 2. Okay, but what you would have done is, let's say you have, imagine it's an exponential, you substitute and you confirm it. If it doesn't work, that you use anything that it can be close to. Okay, so obviously it's increasing, so think about polynomial exponential. So those are the two common one when t is increasing positively. And you will have other functions available to you, probably not circular functions in those ones. Oh well, no, it's actually possible, not in the table of value. So you construct your differential equation, you anti-differentiate. As you anti-differentiate, you get a general solution with a constant. Part B tells you x equals 2 for t equals 0. You substitute and you get the full expression for x in terms of t. Another example. Oh, this example is actually very important. Many times when we had a sac, this is coming every time on the sac for a some sort of any form. And a lot of you can't just come up with a rule. And as you can't come up with the differential equation rule, what happens is you're not able to continue with the actual problem. So this is a typical part that you will see on the application sac. So the way it's laid out is you have the rate of change. That symbol means is proportional to the variable p. So the derivative of p in terms of t needs to be proportional to p. Now what it means is, instead of having proportional, what you can write is an equation, and you would write equal k times p. A k would be a constant that you would be you will need to find out. So proportional means is you multiply by a factor k. So if there's other ways it can be proportional, it can be it doesn't have to be a linear p. It can be a p. It can be a polynomial. It can also be a reciprocal. And in that situation, what you do is you do k times whatever you have written on the right hand side. Okay, so here with this example, the population of a city is p at the time t years from a certain date. Notice the units, so that's in years. Population will be individual, so whole numbers. As you graphing it, yeah, you can treat it as continuous for now. Now the population increases at a rate that is proportional to the square root of the population. So what you do is, when you do proportional, is that symbol, and the right hand side will be just square root of p, p being the population. Okay, And what you do is you write this symbol, and that's not really an algebraic equation, but you transform that into an equal k times whatever you have written at that stage. So that's what you do. You write equal k square root of p. K has to be positive because of the fact that it says increasing. It's increasing. Okay. If it was decreasing, then k will have to be negative. Okay. Now you don't need to know the value of k, so the graph will be it's a sketch. It will be in terms of k as well. Okay. Now it's linked to 9c. You have two different variables. So you have a p here, you have a root p, and you have t. K is a constant. You need to separate the variables. So we bring dt on one side and dp and square root of p on the other side. So the way I would do that is transpose dt on the right and the root of p on the left. So that will give you dp over root p. The k will be transposed on the side of dp, so that will be 1 over k. What's left on the side is dt. You anti-differentiate, dt becomes t. The 1 over root p is a polynomial to the power of negative 1 over 2. You write it as a negative power and you anti-differentiate. So that gives you a rule for t in terms of p. Now, as you want to sketch the population versus time, you need to rearrange that as a rule with p being the subject. Now there's a little bit. You have k as a constant and you have your c as a constant due to your anti-differentiation. You have your general solution. You rearrange it. You make p the subject. There's no substitution in terms of constant. You just leave it like that. C is a real number. That's fine. K is going to be positive, but that's k squared, and that gives you that's a quadratic. That's in turning point form. That's positive, so that's going to go upwards. Turning point form means when you have how does it work out? See, it's actually a bit off. I guess it doesn't really matter. So if you make t equals 0, you get your y-intercept or your starting population, which is k squared c squared over 4, which is positive. We don't know the values, but that's fine. So that's going to be above, and that's a quadratic, so that's going to go increasing as a quadratic or polynomial. Okay. Now c, I was tempted to place c as the turning point, but c is a real number, so it can be positive or negative. So the turning point can be anywhere, either on the left hand side or the right hand side. So it doesn't really matter. You don't have enough information to add anything else to the sketch. Alright, another proportion expression. So here you have another population growth. Population increase at the rate proportional to the population. So now it's proportional to p. So you write dp over dt is equal to, proportional to p means is equal to kp. Because it increases again, k has to be positive. You separate the variables, p on the same side, t on the other side. That is 1 over p dp, that's a log of e. So you anti-differentiate. Notice with the log of p, you don't have to put the modulus because p is a population and it's always positive. So that is the general solution. T is the subject. We need to rearrange that again to make p the subject. That's going to be an exponential. We rearrange that on the left. We have p. Just follow that working out. Now notice what they do is, again, you have a k bracket t minus c. They rearrange or substitute e to the power of k times negative c after you expand the bracket as being a constant, and we're going to call it a. So a is redefined as that constant. that gives you a nice single letter to describe a constant that involve the original k and c. Okay, so a is e of, because it's an exponential, a has to be positive, and a being positive, it's an exponential with k is also positive, so it's an increasing exponential. And for t equals 0, that will be your starting value a being your initial population. Louis, I put that up. There's a link for E11, so start with 15a. 15a is I recorded the lesson on 15a, and you can start the questions. All right. Now you can get other situation a little bit more worded. Okay. So here you have your it's a differential equation using a proportion as well. Okay, so it's given to you that way. What it means is you have a k factor here which is negative. K is positive, but you have a negative in front, so that the negative k is going to be negative. It means it's going to be a decreasing or negative rate of change. All right, so the idea here is probably it would help if I read the question, but have a read. You can pause the video later and have a read, or it's look at example 13. Is h is the height of liquid in the tank, and that's the rate of change of the height in the tank. I put it up here so I can how does it work? No, it's a link and it goes to YouTube. Alright, so the rate of change, which is negative, it's also going to be inversely proportional to the area, the surface area. That's why you have to divide by A. And the surface area A, hang on, is it constant? No, that surface area is going to be variable. Okay, it gives you the value of k. You will need to know some formula for areas. Okay, so here I assume it's going to be circular. Yeah, it's a cylindrical tank, and A is the surface area, so it's going to be in the form of pi r squared. Okay, so you have your drawing here. You have the whole dimensions that will help you out with the conditions. So assume, yeah, it's emptying it. So you start with a full tank or a certain amount. You look at your differential equation, so you don't need the preconditions yet. What you do is you anti-differentiate, so you substitute A by the values, this, and then you will separate the variables. So you have dh for h on the left hand side, you have your t dt, and you have your square root of h. So go back to 9c. If you don't know how to do this, you separate the variables. So how is arranged that way? So it use the reciprocal, then you have the h on the right hand side, the t, you anti-differentiate, polynomial with a negative power, that gives you this plus constant. Okay, and with the initial condition, you know that when t equals 0, it's a full tank, so h equals 1.6, so you can determine the value of c. We substitute into the final expression to get t without any constant or variables, just all numerical values. Okay, and then with the question, it's asking you, there's an actual question, it doesn't ask you to find the rule. where is the question? Okay. Find how many seconds it will take the tank to be empty. So to be empty, H has to be equal 0. So you substitute H equals 0 and you get the T value, that's 15.9. Remember, the 0.9 is 0.9 of not that it matters here because it's to the nearest second. Okay. Alright, I got Isaac attachment, I got Louis, I got Bruce, and I got Monish, and I'm missing Anthony, and I'll have a look at the attachment after that. Yes, of course. Yeah. You can mute me, you can leave WebEx, that's fine. Not the year 12s, I'm talking to the year 11s. Alright, another way when we talk about a differential equation that is proportional to another amount, one that is very applicable is the Newton's law of cooling. So the best example is you have something that is very hot. You take it out of the oven, it's 200 degrees. The room temperature is 20 degrees. If you measure the temperature of your baking, I didn't give it a name, but it starts at T equals 0, it's 200 degrees, and it starts cooling down. The temperature will decrease down to a certain temperature, but because the room temperature is 20 degrees, it cannot go below. So it's an exponential decay, and you will see that later on. That is the equation, and when you anti-differentiate, there is an exponential function. Okay. It's the same, so it doesn't matter. So if the starting temperature is above, it's gonna cool down to the surrounding temperature. If the starting temperature is below, it's gonna warm up to the surrounding temperature. So the surrounding temperature is Ts. dt over dt is the rate of temperature over time, and T minus Ts is the current temperature of the object compared to the surrounding temperature. Okay, so as the temperature gets closer to the surrounding temperature, the rate is slowing down. So the more difference, the faster it cools down. As it gets closer to the surrounding temperature, it slows down. That's the idea with that rate of change. Alright, so again, you will use this equation. What it means is when you write it as an equation, you write equal constant K, brackets, and the difference of temperature. Constant K is a constant, and depending on the you will need some preconditions from the worded problem to determine the value of K. Also remember, when you anti-differentiate, you will get a constant C, so you need another precondition. You need two preconditions to find the two values of the unknowns, K for the coefficient of proportionality, and C, the constant due to the anti-differentiation of your differential equation. Alright, so you have a situation here. The room has a temperature of 20 degrees, so that's the room, so that's the Ts equals 20. The iron bar initially has a temperature of 80 degrees, so that's capital T when lowercase t equals 0, if it makes sense. So that's your initial temperature. Now when the time equals 5 minutes, the T becomes 70 degrees. So those two situations, 80 degrees and 70 degrees, will give you two preconditions to help you to find the values of K and C. Okay. First, you construct your differential equation. So that's going to be, that's not in the right order. All right, that's doesn't really matter. Okay, let's move on. No, well, I mocked up my equation. Let me fix that. was that this one? No. Oh, maybe I didn't have it. Huh. I didn't put it in here. Okay. I don't really want to do it because I don't have pen and paper. So here, your differential equation is going to be dt over dt equals k bracket t minus 80 degrees. Okay. To solve the differential equation, you will anti-differentiate. That will be gives you the t log of E in terms of the temperature. You will rearrange it to make the temperature. So have a look at the work example 14, and then you will get a sketch. It will be 80 degrees. Here that will be 20 degrees, and it's an exponential that's decaying as close as there. Okay. Alright, to find how long the bar goes down, so you make t equals 40 degrees and you solve for time. So hopefully you have that right equation. Now you don't need to use the exponential equation when you have the temperature in terms of the time. You can use the original equation after you solve your differential equation. So you have the time in terms of the temperature in terms as a log expression. You can keep using that, and you substitute the capital T by 40. So that's your 40 here, and you get the time in, notice the units were in minutes, so that gives you the solution in minutes. Alright, now I think that's the last bit. So when you have you can have a different type of differential equation. The left hand side will be the same. Yep, off you go. See you then. It's recorded, so you can have a, I'll put up the link later. Okay. Now, the rate of change can be subject to not just the environment. So when you had the rate of cooling, it's just cooling down, and it will be submitted to only one factor. Okay. You can have a situation when you have two opposing rate of change. So the same idea as let's say your car is moving in one direction. You can have your acceleration that is pushing to increase your speed, but you have also resistance either from the tires or the wind factor that will oppose your that will tend to slow you down. So the idea, you have situations like an object is being heated, so you heat it up, but at the same time it's cooling down. Okay. Population increasing due to the birth, but at the same time is diminishing due to the deaths. Okay. If you put in a container, the container might be leaking out at the same time. Okay. So the idea is, for the rate of change, which is your dx over dt, it's whatever is increasing, take away what's decreasing. Okay. So example, so from the wording of the paragraph, you need to set up your initial differential equation with the conditions, the moving conditions, not the preconditions. So you have a certain radioactive isotope decays at a rate that is proportional to the mass m. So what's decaying is the rate of change of the mass. So it's going to be a dm over dt, which is proportional to m. As it is proportional to m, when you run an equation, that will be equal km. Okay. And that is fine. So that's the rate. The rate of decay is also 2m kilogram per year. Now, it actually tells you the value of k. Okay, so that's your rate of decay. Okay, just be careful. It's a decay. Decay means it's decreasing. So it's 2m, but don't forget to put a negative. If you leave it as 2m, it will be increasing. Okay, so just be careful with the language in the text. So that is your decrease. But what happens is the isotope is formed as a byproduct from a nuclear reactor at the constant rate of 0.5 kilogram per year. So your rate of change is also increasing by 0.5. Okay, so your differential equation, which is your rate of change, has an increase of 0.5 per year, and that's the proportional decay. That's minus 2m. So don't forget that. If you don't set it up properly, all the working out you do after is going to be incorrect. Okay, so here we have that expression. We could have left it like that, but they wanted to write it as a proper fraction without any decimals. So we get that one. We need to separate the variables m and t. So they take the reciprocal. So by taking the reciprocal, we the right hand side do the same. We bring dm on the right hand side. That will get, when you anti-differentiate, that's a log, and that's a log with a negative 1 over negative 4m. So you have a negative 1 over 4. The 2 comes from that constant 2. That will be log of e of the denominator, which is modulus of 1 minus 4m. Now when you take the modulus, I could have changed that to make 4m the subject, but that's fine. Just leave it like that. And the way is to remove the modulus, we introduce that condition. We need to say 1 minus 4m has to be greater than 0. So the 1 minus 4m here is exactly the same as that one, except they went back to the original one and they multiply by 2, which is fine, but it's kind of confusing by changing the expression. Alright, so we have this expression. So we have a C value. We use the original condition stating that if you go back to the problem, is how do we know? Yeah, none of the isotope was present initially. That is a key sentence that tells you that m equals 0 when t equals 0. So all those equations, preconditions, or expressions will not be given to you, handed over as it is. It might be hidden in the text or written in as an English paragraph. Okay. T equals 0, m equals 0. We substitute those values of m and t into here. We get c equals 0, which simplifies greatly this equation. Now we need to rearrange it to make m the subject. That gives you an exponential decay. Okay. Now it's an exponential that is decaying, but it will converge toward that value 1, so it's going to be a quarter. Okay. So we did part A. Why do we need to solve that equation? Is for what value? We did solve now we can sketch it. So that's part C. That's here. So that's 1 over 4 is the 0.25. So that's your horizontal asymptote. You start at 0. So it's an exponential. It goes that way. Now why it looks like way is, remember, an exponential norm e of x will go that way. Okay, because it's a negative t, you will need to do a reflection from the y-axis, and because it has a negative over here, you will also do a reflection from the x-axis. So it will end up going that way. Okay, so I know it doesn't look like a regular exponential, but it's due to the two reflections. How much isotope? Last question. How much isotope is there after 2 years? So when t equals 2, you substitute, you get the value of m in kilograms. Okay. All right. Finally, last example for 9D. Again, we need to set up a differential equation. Again, it will be in the rate of change. It will be an increase and a decrease. Okay. So pure oxygen is pumped into a 50-liter tank of air at 5 liters per minute. Now the units tells you that you measure a volume, the time will be in minute. So liters per minute is the rate of change. Because it's pumped into, that's the increase. And the decrease part is, the mixture is removed at the same rate. Okay, now I will provide you with additional information because that might not be obvious. Okay, so what you're inserting is pure oxygen. Okay, pure oxygen is at it's going to be 5 liters per minute, but once that oxygen is inserted, it gets diluted and mixed up in a 50-liter tank. So what comes out is not going to be 5 liters of pure oxygen. It's going to be a diluted amount of oxygen from that 50 liters. Okay, so the way you do that is to find, so what comes in is your 5. Okay, but what comes out, what you need to do is you look at the amount that comes in of oxygen that comes in, you multiply by Q, which represent the actual volume of oxygen, and we divide by the 50, which is the volume of the tank. That will give you a ratio of oxygen that you have in the whole tank, but it's also as a rate, so it will be what comes out per minute. Okay, alright, so that difference will set you as the rate of change over time, and that gives you your differential equation. I think I have to come back to this to explain it. I've got a few examples with it to explain that part, but I'll do that in another after this video, or in a different recording or different session. Okay, so now once you have that equation, you need to separate the variables. So you take the reciprocal of that becomes the reciprocal on the right hand side. You bring dq on the right and leave dt on the left. You anti-differentiate, that gives you a log. You have a plus c. We know when t equals 0, q equals 11.5. We determine the value of c. That's that ugly expression. You substitute back into here. I think they rounded off to 77. Sorry, no, the 77 here, 77 over 2 is 38.5. They replace the c by a log, and they use the log law with a difference to write it as a ratio. Okay, now what's the next question? Now, if you were to graph it, you will need to re-express Q as a subject. But here the question is, after how many minutes does the mixture contain 50% oxygen? So what we want is find the value of T. Okay, so to find the 50% oxygen, Q has to be half. Hold on, yes, I'm just reading. Yeah, sure, it's fine, Angela, it's fine. They did it a bit something nifty to keep it that way. You know, sometimes the textbook does that. They write it and the work answer, they have a solution that has a weird expression. Yours is different, but it's actually equivalent. Okay, so it's fine. You can replace it. Now, if you replace with an exact, an approximate value, just be careful with the number of decimals. If you use your calculator, don't write it off. Use all the decimals. So store it as a variable and reuse it, and that will be much safer. You will have a better accuracy when you calculate a value. For example, when they ask you for a numerical answer. Okay. So for part B, we continue. So to get a mixture of 50% oxygen, we need to have Q equals 25, which is half of 50. We substitute that into here and we get T equals 4.317. Now, it says minutes, really. You didn't to specify, so I think if you have answered after 4 minutes, I don't see why you shouldn't be penalized. Okay. Anyway, it's a work example. All right. All right. So that's it. Let me stop my recording.